Okay, in part 3, what we're going to be looking at is dispersion and rainbows, total internal reflection, and lenses. So, dispersion is the idea that colors can become separated when they pass through glass because each color has its own speed through a material. So they can go through quartz, and that's why you get the pretty rainbows from a quartz hung in a window, through a diamond, or simply through glass. So anyway, so this is called dispersion. So you'll see your color spectrum, and the idea is that each color takes a slightly different path depending on its wavelength and frequency. Now, smaller wavelengths refract more than larger wavelengths. So in this case, the direction the light originally was going was like this, but it refracted. But you can see the red refracted a small angle, the blue refracted out of its path a much larger angle. So smaller wavelengths refract more than larger wavelengths. I always like to think of it as like kids playing at the beach. And what happens is the kids are playing at the beach, and who gets pushed around by the waves more? The little kid, right? So that's what's going on here. The little wavelengths, the blues, the violets, and stuff, they get pushed around more by, say, water or um, or glass molecules. Okay, so you can see how the red is closest to its original path. The violet is most out of the original direction, right? So it has refracted the most. And this has to do with that index of refraction we were talking about before, only we just gave a general number, but really it would be different for each color through each material, would have a slightly different index of refraction. Okay, so, oh, and will you ever want to buy something that's a high index of refraction? Well, yes, you do. When the optometrist says, "Do you want the high index of refraction glasses?" If you're like me, you're going to say yes, because one of the things is that the higher index of refraction, the bends light better. Okay, it slows the light down, makes it refract more. And so when I had to use glass in my glasses, they were much thicker. And now they're much thinner. I can have almost cute glasses because I've got the high index of refraction material. So even though it costs more, it's polycarbonate instead of glass, it's so much better to wear. And so that's when what they're talking about when the doctor says the high index material, high index of refraction. Okay, now a diamond, remember, slowed light down to less than half of its original speed, right? So light is only going 1.2 times 10 to the 8th meters per second. Still very fast, but it is only 41% of its original speed. So what happens is that the dispersion can be dramatic. Even in a small diamond, you have the colors breaking into different paths. So here we've got red and blue taking different paths. And the diamond is cut so that the light reflects on the bottom of it and reflects back up to the surface and comes back out where it refracts some more. And so the colors keep getting further separated so that even a small diamond has good dispersion of the colors, and that's what's called the fire. And that's based on its index of refraction. Okay, now how do you get a rainbow? Well, obviously we've got the colors splitting, right, into um, different colors coming at us from different directions, basically. What we're seeing when we're looking at a rainbow is the reds coming at us from one angle and the violets coming at us from another angle. Now, notice how you have to stand to see a rainbow. The sun is at your back, okay? Sunlight is coming in and it's refracting and reflecting so that the colors split apart, but also it reflects back into your eyes. So you are standing here looking this way towards the rainbow, away from the sun. So sunlight comes in, and so let's follow the path here of the violet versus the red. So you can see the red comes in, starts to break off from the violet and the other colors, makes this path. And then the blue or the violet splits, whoops, into another path. Goes like this. Bad drawing, but that's the idea. The two colors go in different paths, and every time they reflect or refract, then they get more and more separated, till eventually the violet is 40 degrees out of its original path and reflected, and the red has reflected 42 degrees away from its original path. Now, what that means is that the red is coming down at a steeper angle than the violet. So when you see a rainbow, the red is going to be on top and the violet on the bottom. And that's because your eyeball, so your head over here, is seeing the red coming from a water droplet that's up higher, and your violet is coming from a water droplet that's lower, right? So your violet comes from here, and your red comes from up higher. Okay, so each water droplet basically is giving you a different color. So they don't give you're not getting two colors from one droplet. And what happens is that if there's someone else with you, well, if they're shorter, then maybe the red comes from what was your violet one, and their violet comes from a water droplet that's even lower. Okay, so everybody's going to see the rainbow in a slightly different place. You saw it in this group, and your friend saw the rainbow from red to violet in this second bunch of raindrops. So this color is reinforced by all the raindrops. So all 42 degrees, it's all going to be red drops, and 40 degrees from the sun, it's all going to be the blue or violet drops. So anyway, so the actual rainbow makes a cone shape. And if the ground wasn't in the way, you would see a cone instead of an arc, or you would see a circle. So anyway, so next time there's been some rain and then there's some sunshine, just take a look. Rainbows happen all the time. It's physics. I saw a beauty the other day. They're great to watch. You can even see them at sunset, which is very cool. There's a place I go that I've seen sunset rainbows a couple of times. I'm walking my dog, and they're very high in the sky, and they only have the oranges and reds because it's 42 degrees, but the sun is low. And so that puts the rainbow itself up higher in the sky. It's very cool. Now, so red is on top. That's the primary rainbow. Is your first set of reflections. Now, something else to notice here. You can see these mountains pretty clearly, but you can't see the mountains very clearly inside the bow of the rainbow. And that's because all the water droplets in here are trying to reflect light to your eyes. But the thing is, it's overlapping the colors. So you only see a clear bands of colors on the outside of this region where light is being reflected back towards your eyes. And so otherwise they cross back over each other and you get white, right? They mix back together to make white. Okay, so an observer sees only a single color from any one droplet of water. Your rainbow is slightly different than the rainbow seen by others. You have different sets of water droplets. Your rainbow moves with you because it's not real, of course, so it's always going to stay at that same angle ahead of you. The sun does have to be behind you. The disk within the bow is brighter because of overlapping of multiple reflections and refractions. Okay, so red on top. Here's a lovely rainbow. As you go higher and higher, you will see more of the rainbow. And if you're in an airplane, you might see a completely circular arc. Or here is one that's taken probably from on top of this tower here that you can see the shadow of. So it's, for instance, on top of a mountain, on top of a tower. And then you can see a complete circular arc here. Now, sometimes you will see a double rainbow. Now, the double rainbow, the second one, the secondary rainbow, is usually much fainter. You may only see part of it. But if you see a first rainbow, take a look. There might be parts of a second rainbow there. So Hawaii has lots of rain, and so here it's also an excellent place to see rainbows. And so notice you've got clear vision out here. It's dark in here, and it's brighter in here, kind of whitish, right? Okay, the darkness is because that's where light is actually directed away from your eye. Okay, so what happens with a double rainbow? The sunlight comes in, it refracts, it reflects, it reflects again, and then it refracts again. So you've got two reflections and two refractions. Whereas the single rainbow, right, just had one refraction here, or one reflection, and a second refraction. Okay, so you've got an extra reflection for the double rainbow. And that's one of the reasons that it's fainter, is light tends to leak out at these points where it's reflecting. It may not be totally internally reflected. So you lose a lot of light. And so the double rainbow is usually much fainter. Notice also, though, the violet is going at a steeper angle than the red. And so that means the violet is coming from a higher location on the rainbow. So the colors are reversed. So here you see red on top of this one, but red is on the bottom of this one. Right? Red on top, red on the bottom. So the color is reversed. Okay, some other fun things you may see, usually in the winter, you may see sundogs. And so they may look like little rainbows floating in the sky, but you look in the same direction as the sun. That's why they're called sundogs. They dog or follow the sun. And that's refraction from flat plate ice crystals. And they're really beautiful to see sometimes. They're fun. I see them off at around 4 o'clock in a winter's day. Sometimes you'll see a sundog halo. I've seen these on really cold days because you have to have a lot of ice crystals. And so you have the two sundogs. You might have a sun pillar shooting upwards, and you might have a circumhorizontal rainbow at the top, like that. Okay, so those are fun things to look for. Now, some other stuff in this chapter is talking about total internal reflection, and we're not going to go over that except for the idea that as light reflects from within an object that has a thicker, more dense optical material, so a higher index of refraction, so it's slower in here and faster out here. What happens is that the angle of refraction gradually, as you keep tipping the light greater and greater, because this angle is larger than this one, then eventually it can go all the way to 90 degrees. And after that, it just reflects instead of refracting. And that's called the critical angle. So there's only reflection, whereas normally there's a little bit of reflection and a little bit of refraction for these. And so when you look up into water, some places you can see the sky, and other places it will be reflections of the bottom that you see. So like this turtle, you're seeing reflections of the turtle in some places, other places you're looking out or seeing the rest of the bottom of the pond there. Okay, so there's a whale, same thing. Now the other thing we're going to look briefly at, oh, and by the way, this leads to fiber optics because what happens is that there's total internal reflection. Light beams bounce around in the fiber optics and then come out the end if there's an end. But it's solid glass, it's not a tube. It's because it's a solid glass that it totally internally reflects. Okay, now for lenses. Lenses come as converging or diverging. And for converging lenses, they do what they say. They converge light. Okay, so converging lenses, parallel beams of light come in, and it gets converged down to a point. And this is good for glasses for far-sighted people, because people who can see far away, they can already see really well light that is coming at their face, all right, from far away. So they're already good with their eyeball at taking light that is from far away and focusing it at the back of the eyeball. Okay, but the problem is what they're not good at is taking light from things that are close up. So if they're seeing a flower or something close up, that light going into their eye doesn't focus on the back of the eyeball very well. Their lens usually can't curve it enough. So instead of focusing down to a point, it ends up being broad, which actually my drawing's so horrible here, they both look that way. So the thing is, what they do is you get a focusing lens in there, converging lens, that helps to bring the light a little further in, and then it focuses onto the back of the eyeball. Okay, so the converging lens helps them because their lens is not flexible enough. And this happens especially as you get older, people get reading glasses. What they're having to do is add a converging lens because their lenses have kind of hardened up and they don't work very well anymore. So this can also happen for eyeballs that are kind of short, that they become far-sighted people. Now, nearsighted people, what they're good at is they're really good at bending light already. So they need diverging lenses. So for a nearsighted person, they're already good at taking light from something that's close up and bending it to the back of the eyeball. Okay, so that's their good stuff. But what they're horrible at is taking light that is from far away, so parallel beams of light that are coming in. And those parallel beams of light, their lens focuses it too much. And so it ends up focusing before it hits the back of the eyeball. So this can actually happen for people who have long eyeballs. Um, so what the diverging lens does is the diverging lens, when you put it in, let's make it green, what it does is it helps diverge the light a little bit. That spreads it out. And so it doesn't, so then it will spread out a little more, and then it will focus properly at the back of the eyeball. So anyway, so that's helpful for nearsighted people. So when you're lucky enough to get older and you were already nearsighted like I was, but then your lens starts having trouble with focusing far away things and near things, then you get what are called bifocals that try to do a little bit of both. But for somebody like me, my area of natural focus is right here. About this much space is actually in focus, about 10 inches away from my eyes. That's where I can see things in focus naturally without glasses. So thank goodness for glasses. All right, so what we're going to do is run over and look at some demo over here quickly because we've already been here quite a bit. So what I've got is a laser beam, laser array box, which can make, let's get the Okay, so I've got this laser that I am going to put into some various objects. And so we're just going to take the camera inside. What we've got first here is a mirror. And what's happening is that the light, this is a concave mirror. And you can see how it's like a parabolic mirror. It's focusing the light down to a point, right? So that's a focal point. If I turn this around, then it's a convex mirror, and you can see how the beams of light are being spread out. I'm going to switch to 3 beams. Here is a lens, and you can see how the beams are being, this is a converging lens. Oh, that's what shifted. Okay, so what's happening is the beams are converging to a point. Okay, and I can measure that. It's about 8 centimeters from the laser beam is where it's converging to. Okay, so that's a converging lens, which is a double convex lens. Now here's a double concave lens, and you can see what it's doing is taking those parallel beams of light and spreading them out. And so does it have a focal point? Yes, but it's actually on the opposite side. You have to follow the beams of light backwards to where the point is where it's focused. And I'm going to switch to 1 beam. We're going to look at a prism-like idea. So here is a prism coming in, and you can see how the beam of light incoming is bent and refracted twice there, right? Once in, once out of the prism, and makes it bend. So if you can imagine, this is a triangular prism. That's more than you need here. Anyway, so yeah, so fun to play with light. And that is the end of part 3.